Root mean squared error. In the last few lectures, we were learning about regression loss functions. We learned about two major regression loss functions. The first one being MSE or mean squared error, and the second one being mean absolute error. We discussed that MSE is having a lot of advantages. Similarly, MAE is also having its own advantages, and there were certain shortcomings for MSE and similarly certain shortcomings for MAE. From here on, many of the attempts had been in combining both these techniques and trying to cover up for these shortcomings and trying to take advantages of both the positive points from both the error functions. So from here on, some of the loss functions that we see, they will be kind of how to combine the positives of MSE and MAE and how to make sure that the negatives of MSE and MAE are both taken care of. This is the point. So for this, one major attempt was through RMSE or root mean squared error. So let us see how is RMSE combining the advantages of both these and how is it trying to take care of the negative points. Okay, so we'll first go through the explanation, we'll go through all the detailing, and finally we'll also see how exactly to find the gradient of RMSE, because as a student for you finding the gradient is important. Okay, so let us first find out what is the speciality of RMSE, what is it covering. Okay, so RMSE, this is a, let me write it here, RMSE. This is a very commonly used regression loss functions. So generally, what is a loss function? What does it measure? It measures the loss. So loss means you can say it is y minus y cap or y cap minus y. What is y cap here? Y cap is the predicted value and y is the actual value. That is, if you have any particular data xy in which x is the input and y is the output. Output means expected output. When you're passing the input through your model x, that is your model is m, you are passing x through m, what happens? The model will produce an output which is the predicted value called y cap. But y is the actually expected value, but your model predicted y cap. So the difference between y and y cap, this is what you call as error. This is your error. With this error, we already discussed that simply y minus y cap is not the right way of using error because it may not be best for the computations that we need for the model. That is why we are having many loss functions which are a particular mathematical formulations of this particular value error, right? We already learned about MSE and MAE. Here we are going to see what is RMSE. So first of all, the parameters that we are using, n is the total number of data points. Then you have yi and yi cap. I'll call yi and yi cap. These are for the ith particular data point. Yi is the expected value and yi, expected value means expected output, not the mean. Okay, expected output is yi and yi cap is the actual value, actual output that you got from the model. Okay, so first thing, let us write the formula for RMSE and then start this. So how to write the formula for RMSE? The same way we did in case of MSE. We are going to first find error, then squared error, mean squared error and root mean squared error. If this is your error, what is your squared error? SE or the squared error, you have to simply square this yi minus yi cap the whole square. This is your squared error. Next thing is, what is mean squared error? If you have n different data points, how do you find the mean? If each data point is, let us say, x, how will you find the mean? You will do 1 by n sigma I equal to 1 to n xi. Similarly, for the squared error, if you want to take mean, you apply the same formula. Your mean squared error will be 1 by n sigma I is equal to 1 to n yi minus yi cap the whole square. So this is your mean squared error, that is mean of your squared error. And what is your root mean squared error? RMSE. If you want to find RMSE, you put a square root on this. It is that simple. If you want to find RMSE, whatever we already learned in MSc lecture, the mean squared error lecture, to that if you put a square root, it will be your RMSE, root mean squared error. Now let us see RMS. What exactly is RMSE? You already know it is simply the square root of your mean squared error. So what is the advantages of doing? What is the advantage of doing this? When you take square root, what happens? See, one major problem with MSc or mean squared error was that final output, the final error that you get is not in the original unit of target variable. So your target variable, let us say, is yi cap. So when you are targeting yi and you got a predicted value yi cap and you square this value, then what happens is your error is not in the original units of yi and yi cap. Instead, it is in a squared unit. So interpretation becomes difficult. If you simply interpret the error, that interpretation becomes difficult when it is not in the original unit. So instead, when you take a root of that again, that is you squared it, then you took square root, that means you are back to the original units. So the biggest advantage of using RMSE is that the final output is always in original units. This is the main advantage that you get. We already discussed in case of mean absolute error, your error always remains in the original units. But in case of mean squared error, it gets deviated. It is not in original units. When you have RMSE, this issue is rectified. Now you have final error in the original units. This is the first advantage. Second advantage is it makes this error metric interpretable in the same units. So the reason is same thing, but the point is it becomes interpretable. For you, it is easy to interpret. Then few of the properties of this particular RMSE error. One is that it will always stay non-negative. This holds for all of this. I am just stating as the property, be it MAE, be it MSE, all of these are always non-negative. Still, I am stating the property that RMSE is always non-negative, right? This is a property of RMSE. It always stays non-negative. Second thing is, we already said units are in the same units as that of predicted value. So in the original unit is always maintained. What is the other advantage? Another advantage is it always penalizes large errors heavily. In case of MSc, we had seen that one particular use case of MSc is when you have a use case where you want larger errors to be penalized heavily. The same requirement is satisfied in RMSE. So larger errors are penalized heavily. But at the same time, it also makes sure that the error stays in the original unit. This is the main advantage. Even after penalizing the larger errors heavily, final error value, that always stays in the original units. Okay. So you already know if you have RMSE 0, that means it is perfect prediction. One more advantage is, what if you differentiate it? In case of MSc, you had seen that it is differentiable everywhere. But in case of MSc, it was not differentiable at x equal to 0. Everywhere else it is differentiable, but at x equal to 0, it was not differentiable. What about RMSc? This is also differentiable everywhere. This is one major advantage. So you got the advantage of MAE, which is that it stays in original unit. You also got the advantage of MSc, that it is always penalizing the larger errors heavily. You got the advantage of both, which is it always stays non-negative. Plus, you also got the additional advantage that this new thing always stays differentiable. Right? So these are the advantages. At the same time, what are the problems? One is that it is sensitive to outliers. So this thing we already discussed when we were discussing MAE and MSc, that robust to outliers or sensitive to outliers. Which is better? This depends on your use case. In some use cases, you may want it to be robust to outliers. That is, even if there are outlier points, you should not penalize these larger errors heavily. Sometimes you want it to be sensitive to outliers. That is, if you have points which are larger away from the mean, or if they are larger errors, you don't want it to be penalized heavily. So this is a decision based on the exact requirement of the use case you'll have. Okay. Then one more problem is, we said it is easier to interpret because it is in the same units as the original unit. Whatever be the original unit of yi and yi cap, your final error is also in the same unit. But another angle of seeing interpretation is, how can you explain this to a layman? If you have a non-technical person and you want to explain this is my error, from that angle, how interpretable this is. This is where RMSE becomes even difficult to interpret compared to MAE or MSE. In case of MAE, it's very easy to interpret mathematically. In case of MSE, it becomes a bit more difficult. In case of RMSE, it's even more difficult to interpret from this particular angle. If you're trying to explain it to a non-technical person, it becomes difficult. Before we get into the gradient, I'll just make one more point. That is, when should you use? Which particular situations should you use root mean square error? So one common use case is in regression tasks. Whenever you see regression tasks, something like maybe house price prediction, or maybe stock forecasting, these sort of things. These things, regression tasks, you generally go for RMSE, root mean squared error. Second is, whenever you want interpretability in the original units. And what is the other point? You want to penalize large errors heavily. Okay, large errors you want to penalize heavily. These use cases you generally use root mean squared error. One point I want to make clear here is how to find the gradient of RMSE. I told you that it is differentiable everywhere, but I want to show you how to find the gradient and how is it differentiable everywhere. Okay, and then we'll see what is the advantage of that gradient. We'll also compare the gradients of MSE, gradient of RMSE, etc. Why are we talking about gradients here? The main reason is, coming to building any particular machine learning model, gradient plays a big part, because gradient is what decides how much you adjust the error. That is, each time when you are training the model, in each step, how much should you improve your existing value? This is decided by gradient if you are using gradient descent. So let us see how to find the gradient. First of all, I'll write loss of y and y cap. How is this loss written? Loss is this particular function. So I will write it here, root of 1 by n sigma I is equal to 1 to n yi minus yi cap the whole square. This is the formula for RMSE error. So you call it error or loss. Both are one and the same. Okay. What I'm going to do here is, first of all, I'll take the MSE term out. This term is MSE term. I'll write it as M. My MSE term, this part is 1 by n sigma I is equal to 1 to n yi minus yi cap the whole squared. This is my MSE, mean squared error term. So I can write loss, that is this loss, I can write it as root of m, right? If m is this and my loss is this, then I can write loss is equal to root of m. What is it that I want to find? I want to find the gradient with respect to yi cap. Yi is one particular prediction. With respect to that particular prediction, I want to find gradient. So what will I do? I want to find del L by del yi cap. This is what I want to find. Here I can make use of chain rule. How will I make use of chain rule? I can write this is del L by del m into del m by del yi cap. This is how I can use the chain rule in order to do this differentiation. Here what is this term? Del L by del m. Here L is equal to root m. Because L is equal to root m, del L by del m, this will be equal to 1 by 2 root m. How is this 1 by 2 root m? Because if you just have root x as the term, How, if you differentiate root x, what will you get? You get 1 by 2 root x. The same reason here, root m, so del L by del m is equal to 1 by 2 root m. What about the next term? Del m by del yi cap. So the first term, you know, it is 1 by 2 root m. So you can write this as 1 by 2 root m into del m by del yi cap. Next term is del m by del yi cap. If I do this, del m by del yi cap, what will I get? M is this term. If m is this term and I differentiate, it will be 1 by n, we can take outside, then it will be yi minus yi cap the whole square. See, even though there is summation, only one particular term in that summation will be corresponding to yi. So only one particular yi minus yi cap will remain. So this is a squared term. When you differentiate, 2 will come in front. Then you have yi minus yi cap. This is what remains, right? So ideally there should be a negative sign. What I'll do is, instead of putting the negative sign, I'll make this yi cap minus yi. Why should I just play with a negative sign? Yi cap minus yi. So think all these formulas, instead of yi minus yi cap, it is yi cap minus yi. Okay. So both will give you the same result, because anyway you are squaring, the negative won't hold. In order to remove that negative from derivative, I am making simplifying this. I am just writing it this way. Okay. So then if I do, what will it be? This is equal to 2 by n into yi cap minus yi. If I substitute this here, what will I get? Here I can put 2 by n into yi cap minus yi. If I do this, then both these 2's will cancel out. Both the 2's will cancel out. Then I will get yi cap minus yi divided by n into root m. What is root m? Root m is your loss L. So I can substitute L here, which means my final answer will be yi cap minus yi divided by n into L. So I'll write it here. It will be yi cap minus yi divided by n into L. This is the gradient of RMSE error. This is differentiable everywhere, but few things that we want to understand about it. First thing is, when you found the gradient of MSE, this gradient was growing linearly with size. That is, whatever with the error yi minus yi cap, the gradient was also growing linearly along with yi minus yi cap. See, error grows in a squared manner. So gradient, which is the differentiated term, which will grow linearly. What about this particular RMSE error gradient? What about this gradient? Is it also growing linearly with respect to the error? No, it is not. Here, it is not growing linearly with respect to the error, because you have a normalization with error term here. Whatever be your loss, that is coming in the denominator. That means when your loss increases, this term will increase. This term will increase, but that is normalized by this loss term in the denominator. What happens because of this? If there is a larger error, the change that you are going to make in the value of your parameters of the model, that won't be as large as what will happen with MSE. In case of MSE, if one particular example gave you very large error, what happens? Your model parameters, the parameters of your model will face a larger change. But in case of RMSE, because of the presence of loss in the denominator, even though the numerator term increases, that will be normalized by the denominator term. What happens then? The change in model parameters in case of occurrence of a large error won't be very large like MSE. Instead, that will be a nominal change. This is what happens with RMSE. So this is what you have to practically understand. When you have a model and you are changing model parameters according to the gradient descent rule, the gradient of MSE will actually grow linearly with error, but gradient of RMSE is not growing linearly with the error. That means the change in model parameters will be comparatively smaller. This is the speciality of RMSE. So somewhat you can understand that RMSE combines the good parts of MSE and good parts of MAE, but there are certain disadvantages, or you can see certain specialities which may sometimes be advantages, sometimes be disadvantages. We'll move on to the next loss function in the next lecture. Once we cover different loss functions, we'll compare all those and see which one is to be used at what point.